ready? There we go. All right, guys. You've all seen me here this week. I'm going to talk to you a little bit about electrical safety. The purpose of this trailer is to show you what effects electricity has on the human body. We'll give you some safety tips. All of you here are either old enough to drive or will be shortly. So you will want to pay attention to those safety tips. You heard some from Tracy Fougere with Basin Electric earlier this week with the story behind the switch. Now what we've got here is we are plugged into a transformer right over there by the cabins. It feeds a normal household voltage out of that transformer, 120, 240. What we do is we bring it back into another transformer that is just like what would be on a power line that feeds your house. Transformers do not care which direction electricity comes in and goes out of. It makes that piece of equipment no difference. The other purpose of this trailer is to show you that, so that if your folks or you at a later date have a generator, to know just how dangerous that can be for Jason here, who works for Yampa Valley Electric, or myself, I work for YW Electric. I started my career as a lineman in the industry. Now I'm a member service rep. Jason is a lineman, and that's what he does for a living. You want to show him an arc, Jason? Okay. What we've got on this power line here is 7,200 volts when I push this button. Hot. Dead. Can anybody tell me approximately how hot that arc is?
Very.
Very is correct. It's not quite 6,000, it's approaching 4,000 degrees. Now the other things that we've got up here are some safety equipment that both Jason and I are wearing. The glove that I have on here is a low voltage glove. It's rated for 600 volts. It is tested to 5,000 volts. It might look like a dishwashing glove. It is not. We test these gloves every 30 days of use. The glove that we have up here on Mr. Sparky, you can see has reject road on it and in white letters. And I've got a whole pile of them here. You guys want to take a couple of them and pass them down around so you can look at them a little closer than you did with Tracy's piece. And you may notice that a couple of these have burn holes in them. They have been used for this demonstration before. We'll get to that in just a minute. What these gloves are made out of is a natural rubber. They're very soft. You'll notice that Jason's got leather protectors over the outside of his gloves, and I have a leather protector over mine as well. What can happen with these if we're working on conductors or crossing a fence, anything like that, anything that's sharp, the leather protectors will kind of protect the glove, but it's very easy to cut this leather. It's got to be soft so that we have some dexterity to work on things. With that, it'll poke a little bitty hole through that glove. Let's show them that the glove is good, Jason. Ready? Hot. Jason's going to touch all the way around the thumb on that glove. Just like we were working on an energized conductor. You can see it's not doing anything. Dead. Now what I'll do is take this little push pin, like what you'd put on a bulletin board to put your piece of paper or your pictures up there. I'll put a small hole in this glove. Right on top, Jason. That hole is about like what would happen if we were crossing over a barbed wire fence or handling the end of a conductor with a burr on it, and it would cut through this leather and make a small hole in that glove. As I said, we test these gloves every 30 days. That's a professional test that we do. We also use an air test every time before we use them. And like Jason's gloves and those gloves that I passed around, if you notice, they're black on the outside and they've got yellow in the middle. By doing that air test, it blows them up like a balloon. And it'll stretch the rubber out on there. If we can see that yellow from the outside, that means we cannot use that glove. Okay, I'm going to give it a shot and see whether my hole works. Hopefully it don't make a wire out. Come on, hot. There you go. Yeah, hit it again. It ain't gonna work. But did y'all see that pickle light up like a light bulb there? They make a very impressive show. That little bitty hole turned into a big hole in that glove. That's just like if we were working on a piece of equipment and we touched ground. Most of the time we do our hot work out of a bucket truck that is an insulated truck. That's another layer of protection so that that doesn't happen. Now if you do happen to have a hole in a glove that you don't notice when you're doing your air test, you can feel just a little bit of a tickle if it jumps through your glove. So I've been told. I have never had it happen to me, but I've talked to a couple of guys that have. The first thing that they do, since they're standing in that truck, is they get clear back away from the conductor, go back down to the ground, test their gloves, and most of the time they have to have another pair of gloves on before they can go up and do any work. It's very easy to miss some of those small holes. That's why we have so many layers of protection. Now what I'll do, where that pickle was at, I'll put this chicken leg. This chicken leg has got the same basic parts in it as the human body. It's still got nerves in it that are attached to the muscles. It's got a bone, it's got bone marrow, it's got skin, and it's got fat. This is probably the most realistic show of what electricity does to the human body of anything I've ever seen. This time Jason will work on the hard hat.
Okay. Do it on the hard hat.
Test it first,
Okay.
and then we'll knock it off with the lead. You'll also notice that Jason and I are wearing hard hats. These hard hats aren't just for when somebody's working above us and drops something off of a pole or anything like that. They're not really meant to be dielectric protection. It's kind of a side effect. Sometimes we're so involved with our work that we may get a little lax and not notice how close we are to an energized conductor. But it's just another layer of protection for us. You can see that hard hat is really dirty. Looks like it's been drugged down a county road for a couple miles. Hot. You see, as Jason's rubbing around on there, it's not doing anything. Dead. Go ahead and knock it off there. Oops, we just lost our hard hat. Hit that several times. Okay, it should be cooked now. You notice on that chicken leg how all that muscle balled up and it pulled the tendons in two. Tracy explained to you guys that the human body works on electricity. Now, I'm not going to go grab that chicken leg just yet for obvious reasons. It's hot. But here in a little bit, what I'll do is I'll take it off of there and I'll put a grapefruit on it, and in a little while after it cools off some more, I'll actually break it in half so you can see what happens to that bone. But the way electricity attacks your body is first thing it attacks is your nervous system. Us in the power company industry wish that we could find a conductor that is as efficient as the human nerves are. We would have virtually no line loss, which would equate to cheaper power for you. Every company pays for line loss. The next thing that the electricity does to the human body is it attacks your circulatory system. What does your blood have in it? Can anybody tell me? Iron. Very good. After it gets your blood vessels and stuff dried out, then it attacks the muscles. The last thing it usually attacks is the skin, other than the entry and exit point. And this grapefruit that I'll put up here is a very good show of what the entry and exit points look like. Everybody see that little bitty hole that what it turned into? If we want to take a look at that, it'll be sitting right up here later. You can see it didn't really do a whole lot to the hot dog in there. Hot dogs are very wet. If I put it down there, it'll actually just about blow up like it does in a microwave. Oh yeah, that took that good.
Do the head again.
Yeah, we can go ahead and do that. I got a little malfunction with my rubber glove. Okay, everybody watch the grapefruit really close. It should glow like a light bulb. Ready? Yep. Hot. Okay, that's good. You see it shooting the steam out of that grapefruit? That's at almost 4,000 degrees for you. Also, we got the cantaloupe pretty hot. Mr. Sparky is officially smoking. This I can still grab with glove on. If everybody sees that little hole, there's one just like it on the other side, where it's burnt, where that arc was coming out of it. In just a bit, we'll cut that open. This brings me to a good point to talk about what happens when electricity goes to ground. If a line lays on the ground and the conditions are right, you guys all saw the pieces of sand that Tracy had. This is one of the more impressive ones that I've seen. We had a call from a consumer that said, a line's been on the ground for a couple of weeks, and he just remembered to call it in. We went out and looked at it, and it had laid in snow for a while. Snow finally melted, and it was on top of sand. And this is where the wire ran through there. The people at the other end of the line still had power when we shut it off to fix this. It's kind of impressive, huh? That's why we tell you, do not go near a down power line. When electricity goes to ground, it does not just go to ground in that one spot. As Tracy was telling you guys Sunday night. What it does is it spreads out in the ground. And what it makes is what we call step potential. You've all have dropped a rock or threw a rock out in the water, and then when that rock goes in, it makes the ripples as it's going out. Imagine those ripples as a different voltage in circles. Well, what happens if if both of your feet are at the same spot? There's not a very good chance of much difference in potential there or voltage. But what happens if you step across those imaginary lines in the ground?
Makes a circuit.
That's right. It goes up one leg and down to the other. Which is why, if you're in a car accident and run into a pole and knock the line down on top of the car, we do not want you to just open the door and step out. Once again, there you're making a circuit from your car to the ground. Your tires do have somewhat of an insulating effect. They will insulate a little bit, but what they do is they continue to bleed electricity over from the rim to the ground because they're dirty. They've also got steel belts in them. When the tire gets hot enough, what happens is they'll blow out. Let all the air out, then the car settles down. At that time, most generally, the line will trip out. But sometimes it may not, depending on the way that the circuit runs. And Tracy told you guys if you had to get out of a vehicle that's in contact with a power line to hop, that's a very good idea. At least 40 to 50 feet away. It's always better to stay in the vehicle or piece of farm machinery until one of us guys gets there to make sure that the power is in fact off. We will let you know that. Y'all want to see another pickle light up?
Yeah.
My hands are sweaty.
Those aren't for the barbecue, are they?
No. Here it is. Cool enough now? Okay. This is a good one to show this. Since my hands are already dirty with pickle juice, I'll show you what this does to... Y'all could see that before, that the tendons had all pulled loose from one end of the chicken leg. What happens there is the muscles contract hard enough to pull tendons in half. If you see the end of that bone, it is no longer bright, pretty red like bone marrow should be. That's because the electricity has went through the middle. And it also makes the bone really brittle, because it actually fractures the bone too. As you all notice, I am wearing a prosthetic arm. About 10 years ago, I was working in a substation and we had a little bit of an error on a switching order. We had one step that was missing. And I contacted 12,470 volts between my shoulders. I was working on a ladder and my left hand was grabbed onto the steel substation bank, which is grounded. You all can imagine what that does. My left hand looked like overcooked French fries that you would get at McDonald's or Wendy's, what have you. There didn't look like there was much the matter with my left arm, other than my hand. I had a spot on the back of my left shoulder and a spot on the back of my right shoulder. That little spot that was slightly bigger than this on the back of my right shoulder is now about the size of a basketball from all the tissue that it burnt in there that it affected. The burn unit is not a fun place to be. I can speak from experience. If you can keep from getting burnt, it's a whole lot better off. This grapefruit is past what I would call edible. See what happens to the inside of the grapefruit. That's a pretty good show of what electricity does. Get it, Becky? Okay. Electricity does a lot more damage on the inside than it does on the outside. Everybody get it? See how it turns everything in there all black?
Oh yeah. Wow.
The rind of a grapefruit is really close to what connective tissue is in the human body. And see, there's so much of what would be the nervous tissue in the human body in there. We can't sustain an arc up here long enough and maintain our equipment to totally dry this grapefruit out.
Yeah, you
Should I say it's a little past edible?
No. That's just the way I like it.
Okay, does anybody have any questions about the high voltage demonstration that I've just done? I'll move on to a little bit of household voltage stuff. If you got a question, blurt them out. Dang, I must have done a pretty good job of explaining it if nobody's got a question. You'll notice before I'm ever going back to work with my rubber glove, I'm making sure I put the protector back on it. You all have seen these funny looking outlets before that got the buttons on them, right?
Yes.
Did somebody have a question down there? Uh-huh. What the hats are made out of is it's a little bit harder plastic than an ice cream bucket would be made out of. They're kind of the same material. I believe, yeah, they say high density polyethylene, HDPE. They don't put much more than that on there. These are kind of cheap insurance for a power company. Plus they're required by OSHA, the Occupational Safety and Health Administration. But anyways, as I'm saying about these funny looking outlets that got the buttons on them, what they are called is ground fault circuit interrupters. They are made to trip in less than 1/10 of 1 second if they sense a difference in the current from the blind side to the neutral side of the outlet. It's kind of the same thing as a car battery, positive and negative, except for we're working with alternating current. The current runs each way 60 times in a second in the United States. So 1/10 of 1 second they are supposed to trip if they see any difference between the two sides. The round prong is the ground prong. It doesn't measure that. You'll also notice on them, if you look really close, there's one of them legs that is thin and one that is thick. Not as in the actual thickness, but the height. What we've got here for a demonstration is this old drill that we see a lot out on ranches. These things are quite old. They don't make them with metal cases anymore. And I'll show you why. This one has been updated because the cord was bad. Somebody went and put a brand new cord on it. You see where that third leg is supposed to be on there? The ground prong? Somebody took that off. Now why do you suppose they would do that? So they could put it in an old outlet. If you put this thing in the old outlet, and you get lucky and get the polarity on it right, so that what should be the neutral side of the plug happens to go to the neutral side of the outlet, this case is effectively grounded through the neutral. On our electric system, the neutral and the grounds are tied together. I'll plug it in what should be the correct way. Get the cord out of the way. See, the drill works. I can touch it to our grounded trailer and nothing happens. Now imagine you just broke that ground prong off because you're on an old outlet and so you want to plug this drill in. And you don't pay much attention, or somebody has wired the outlet incorrectly. Another trick that we have seen is people will take their file and file the wide prong down so it's the same width as the narrow prong. So it'll go in those older outlets. What happens then is it's really easy to turn that around and get it backwards. You have to push kind of hard, but it will go in there. You also notice when I'm picking this up, I'm wearing my rubber glove. Now when I pull this trigger, it completes the circuit in the drill. That case is hot. Uh-oh, we just tripped the ground fault circuit interrupter instead of me getting shocked. The reason we added this portion to our demonstrations, this is about 10, 12 years ago. We had a gentleman in our service territory that was drilling holes in posts, standing in water, building new corrals. He was found still with the drill in his hand. He did not live. The household voltage killed him because of the current. The body can withstand a lot of voltage. Who in here has ever touched an electric fence? How many volts do you suppose an electric fence has in it? How much? No.
1.
Try about 35,000.
Okay, yeah, you're right.
That's exactly right. They pulsate too. That way you can let go, or an animal can get away from them. There is very, very little current in an electric fence. Somewhere to the tune of like 1 to 5 microamps on a lot of the newer ones. Some of the older models, they were made before the safety regulations. So they had enough current in there, and if the pulsator in them stopped, it could actually kill you. It only takes 2 milliamps across your heart to put it into ventricular fibrillation. When you hear them on ER and Grey's Anatomy and those kind of shows talking about charge to 300, charge to 600, that kind of thing, what they're talking about is charging to that many microamps. And you see what that little bit of power does to the body when they're on the table. That really happens in real life. People jump. Not quite to that extent that they do for television, but the whole body will jump. And that's how they're starting the heart up. It's just the opposite with that thing. It will put your heart into just basically a quiver mode where it will not pump any blood. Does anybody have any questions about that? How are we doing on time? Okay. If nobody's got any questions, The only other things that I can say is you as the general public are a lot more eyes in the field than Jason, the rest of his co-workers, or me or the rest of my co-workers are. If you see a power line down, you can always get a hold of the non-emergent sheriff's office number in your area. They report those kind of problems to us as power companies. I know at this stage of your life you probably don't want to be on a first name basis with the police department. But that is a very good way to report hazards in the field. Other things that we see as a problem out in the farm and ranch communities on the east side of the state where I'm at is people that stack their hay bales right next to a power line. What'll happen is kids will go out there and decide that they want to go mess around on the hay bales. They'll crawl up on them. And if they're too close to the line, it is very easy to get, to fall off of the hay bales, get into that line, or stand up into it. There's been more than one report of that. In eastern Nebraska, where I grew up at, we used a lot of aluminum irrigation pipe. We laid out on the ground, and instead of using an irrigation ditch, we opened a little gate valve on the pipe and let water run down to water the crops. The handiest place to stack that stuff always is on the end of the field, right by where the power line runs. If it's sitting there all winter, rabbits or skunks or that kind of thing will get into the irrigation pipe. You'll stand it up to dump it out. That piece of pipe is 30 feet long. Our lines are only 18 to 20 feet off the ground as a general rule. Sometimes they're a little higher than that. You can see the difference in just the math there, that pipe will very easily touch that wire. If you're standing there holding on to that piece of pipe, that is a very good conductor. That aluminum is the same thing our wire is made out of. It'll carry the electricity right back down to you. How many of you grow up on farms or still live on a farm? Do you ever have to move grain augers around at harvest time? Put grain in any bins? Grain augers are probably one of the most common pieces of farm equipment to get stuck into a power line. Years back, there was a lot of people that moved the smaller augers by hand. That's just a big piece of metal that's going to get into a line and hurt people too. Tracy talked about kites and how the string can be conductive and bring that right back to you. Power line's a good thing to stay away from as far as that goes. Yes?
How do birds stay alive?
Very good question. She asked, how does a bird stay alive sitting on a wire? The reason a bird can stay alive sitting on a wire is you see how far apart they are. As long as they're not touching both, they can sit there and not ever know that anything is happening. It's just like they're landing on a tree branch. What's that? Pardon me? If the conductor's big enough, but we've got in the town of Akron, I have seen squirrels running on our power line. They'll run right down it.
Just as long as they don't touch both, right?
That's right, just as long as they don't touch both. Yes, in the back. Mm-hmm. Most of the time there has to be something else there for a squirrel or another animal to touch. A lot of time you'll see that happen right by a pole. And if the insulator on the pole is just bad enough that there's a difference in voltage where he steps off of the wire onto the cross arm, or if the cross arm's a little bit wet, anything like that, the voltage can run right through him and it goes to ground right there. as you know, pieces of glass, and what that is it's ceramic, like you'd use in art class. I can't. It's been so long since I've been in art class that I can't remember the name of what the particular kind of clay is. One of them that we use is porcelain, and I cannot remember the other synthetic one. But it's got voids in it. And what actually does the insulating on one of our glass or porcelain insulators that we use is the glaze on the outside of it. It makes that clay shed water, so it doesn't become conductive. Well, if we nick that when we're putting that on there, it just gives that insulator a chance to absorb water. And then it'll track through and it'll be a bad spot there. Voltage will bleed off to the crossarm. Is there any other questions? We're about out of time here.
Okay.
Thank you for your attention.
Yeah.